getting started with the first session on remote sensing data and nuances. Firstly, I want to convince you for this tutorial that remote sensing is not just interesting from the perspective of applied machine learning. So it's not only interesting from taking models or existing methods or developing some variations of existing methods and applying that to remote sensing data sets. It's also interesting as an entire data modality on its own for machine learning. So just like we have images or text or video as different data modality subfields in machine learning, remote sensing data is also its own modality and comes with a lot of really interesting foundational research questions as well as applications within that space. So my hope is that in the future, like we have natural language processing now, in the future, maybe we'll have a whole subfield of machine learning of planetary data processing. So to make this parallel between remote sensing data and traditional data modalities more clear, I'm going to give a couple of examples here. So when we're working with image data, we typically have a very large set of independent samples. For example, ImageNet, we have a very large data set that we can use to train the model. And then we can use that model to make predictions for a much smaller data set, usually one sample at a time. And then we can use these models for real world use cases, like, for example, detecting obstacles for a self-driving vehicle, where we want to know what are the obstacles in the road given an image, for example. With language data, we have a very large data set of variable length text sequences that we use to train our model. And then again, we have, when we've trained this model, we can use it for inference to make predictions on individual samples again. And generally, these are kind of independent samples. Maybe they're coming from the same voice, but we're asking different questions, or it's really being evaluated one sample at a time. So then we might use a model like this to, for example, get a response from our Google Home about what the weather is going to be today in New Orleans. So with satellite data, we have the same parallel pipeline, but there's a really interesting inversion where we typically are training on a pretty small relative to the total available data set of labeled data. And these data are extremely sparse compared to all of the data that we have available from satellites orbiting the planet. So for example, even if we had, let's say, 5,000 examples of satellite images of maize fields, and we wanted to train a model to detect maize, this is still an extremely sparse sampling over the entire variability of maize fields that we'll see across the globe, both in space and in time. So we have a huge amount of data that we're never going to sample with our labeled data sets. And so with these satellite data, when we're using satellite data at inference time, generally we're not making predictions on individual samples that are treated independently from each other. We're taking a model that's been trained on these sparse labels to make very dense predictions that together make up a map. So rather than taking one image from here, one image from there, usually we're trying to make predictions over an entire contiguous area. For example, the entire country of Kenya. We want to make predictions about where maize is growing or what the expected yield will be in these maize fields. And so when we make these predictions, we stitch them all together to create a map. And that is the output information that's given to end users to answer questions like, what is the maize production going to be in Kenya this season? What we're going to be talking about in this kind of the outline for this session is, what is remote sensing? How are we using remote sensing data as inputs to machine learning models? How are we using these outputs from the models? And some important considerations for using these data. So let me just hop around here. So firstly, what is remote sensing data? It's these data sets that are collected by satellites. Also, remote sensing also includes drone or aerial images and other kinds of sensors as well. But here we're just talking about satellite data. So these satellites are orbiting the Earth and capturing images or other kinds of observations at regular intervals. So let's say every 5 days or every day, a location might be imaged by a satellite. And so these images are collected all the time, everywhere. Or they're collected on a targeted basis. So there are some satellites that are tasked, is what we would call this. So you say, I want that satellite to take a picture of this place on this date, and then you just get that one image, compared to these other satellites that really just scan the Earth constantly. And this is really different from traditional data sets that we're used to working with in computer vision, where we have these data sets that where samples are collected randomly and independently, and we don't have this global and consistent coverage. So as an example here, I'm showing the distribution of images in ImageNet and COCO, where we have images that are basically wherever they were from in the images that happen to be obtained for that data set. And this is a really big difference with remote sensing data, and actually a place where remote sensing data can be really powerful in terms of constructing data sets for foundational research, because we have the ability to create whatever data sets we want. So, these data sets are being constantly collected over the entire globe. And so if I want to collect a data set where there's some domain shift in time, because I want to study distribution shift and robustness to distribution shift, I can actually go get that real data by taking all these locations and getting the satellite data at different points in time or in different years, or from different satellite data sets or at different locations. So there's this huge archive of data that's available that we can sample to construct whatever kinds of information we want to have in our data sets. That said, getting the labels for all of those data is a whole other problem, but Catherine is going to talk more about that in her slides. So to construct these data sets, we don't have to go crawling Flickr and hoping we find what we're looking for, or we don't have to go take a bunch of images in our lab or go around the world to take certain images on the ground. We have these data sets that are already being collected constantly everywhere in the world over time. So when we're looking at satellite data, there are 3 really important dimensions in the data sets. So we have the spatial dimension, spectral, and temporal. And so the resolution of the information in each of these dimensions is going to be driven by the instrument that is on board the satellite. So the kind of camera it has, if it has a telescope on it, what sort of lens and whatnot, the altitude that the satellite is orbiting at. So the lower the altitude or the lower the orbit of the satellite, you might have higher resolution images because you're closer to the ground. And if you have a large number of satellites, is what we would call a constellation. So if you have many satellites, you can cover more of the Earth every day and get a higher temporal cadence. And we'll talk more about each of those dimensions in a minute. So there are literally hundreds, actually thousands of satellites orbiting the Earth right now, and that are continuing to be launched all the time. Not all of these are imaging satellites. There are a large number of them are communication satellites. A lot of you might have heard of Starlink, which has a lot of satellites up. And so they're all in different orbits. Most of the ones that we're using for imaging, for creating these data sets, are in a low Earth orbit. So they're kind of lower than, for example, GPS satellites. And these data sets are enormous. So you can imagine if you're constantly taking images of the Earth all the time with hundreds of satellites over many years, the volume of data is enormous and is continuing to grow all the time. So from a company called Planet Labs that images the entire planet every day, they're getting, at least this is actually an old statistic as of a few years ago, they're getting 11 terabytes of images per day. And now, this was back when they only had like 4 bands on their satellites. Now they have 8 bands and even more satellites. So you can imagine how enormous these data sets are growing. And so all of these satellites, depending on what sort of sensor they have, are able to see in different wavelengths of the electromagnetic spectrum. And which wavelengths they're seeing in tells us different information about the Earth's surface, or about what is on the Earth's surface, or in some cases below. So if we look at our familiar electromagnetic spectrum here, you can see in the little visible light sliver, that's where we're used to working in computer vision. This is where ImageNet, COCO, et cetera are. But our Earth observing satellites are imaging in that space, but also way out into near infrared, mid infrared, thermal infrared, radar. We're collecting all kinds of observations in additional bands. And so typically a satellite will have like at least 4 bands, but might have up to, 30 or even more if it's hyperspectral. And just for contrast, if anybody looks at astronomy data, there are astronomy satellites that are generally pointed in the other direction away from the Earth. And often those are looking in kind of the other side of the spectrum. But again, this is all based on like, what are the physical interactions of light that's coming from either the sun in terms of passive sensors, or from an emitted radar wave in terms of active sensors. Whatever electromagnetic radiation is being emitted and interacting with what's on the surface and being reflected back to the sensor, that's going to determine what we can actually see in the image. And so we'll see things like, depending on where we're looking in the spectrum, we can measure the reflectance of the surface. This is what we're used to thinking about with normal images. We can see moisture or like water content, the elevation or slope of a surface, the roughness of a surface, temperature, all kinds of information that we can sense beyond the visible spectrum. So as a result, our data sets have these several dimensions of XY, which we also have, 2 spatial dimensions traditionally in our computer vision data sets. And we have this wavelength, which is just RGB traditionally. So for example, in this COCO test image on the right, but we have many, many more of these bands that we want to look at in these remote sensing data sets usually. And in addition, we have this time component. And depending on the temporal resolution of our satellite data set, this could be quarterly, so maybe we have 4 images per year, so that dimension is 4. It could be monthly, it could be daily, this would be 365 dimensions. All of this is configurable based on how you create your data set. So there's a lot of freedom to create new kinds of data sets and resample the data in however you want to do for your application. So spectral resolution describes the number of bands and the coverage of the spectral bands on the satellite. So this is going to vary pretty substantially between different satellites. Some of them have overlap, and some of them are designed to be to have good overlap in at least some of the bands to reduce the domain shift between different sensors. But there's still a lot of variability. So each row here is showing example spectral response in the near infrared and visible wavelengths for some commonly used satellites. In particular, the bottom 3, Landsat, MODIS, and Sentinel, are really commonly used satellite data sets. And so you can see how the spectral response varies across all of those satellites. And a lot of them have pretty good coverage in the visible and mid-infrared, or near infrared. But as we get out to longer and longer wavelengths, it kind of starts to vary. So here in mid-infrared, there's a good amount of overlap still. But then in thermal infrared, for example, Sentinel does not have a thermal band. Some of these, like if you're trying to sense thermal infrared, for example, is really important for looking at geochemical constituents, like what is the mineral content of a surface? You know, maybe if you're looking at geological components in the earth, versus like shortwave infrared is important for looking at water content, especially in leaves. Radar is important for looking at textures, or looking, for example, for water. Radar is really good because the smooth surface of water reflects the radar waves back in another direction. And so, you know, depending on what you want to actually observe, will influence which satellite data set you'll be able to use. So this is an example of how a certain region looks in these different satellite bands. So in grayscale, so you can see blue, green, red are what we're used to working with. And then as the wavelengths get longer into near infrared, shortwave infrared, we see that different pixels on the surface are brighter or darker in these different wavelengths. So spatial resolution is the area on the ground that is covered by each pixel. So if we say a satellite has 1 meter per pixel spatial resolution, this means that every pixel in the image corresponds to a 1 by 1 meter square on the ground. And so you can imagine that that's really going to influence what you can see and what you can make predictions about in your data set. You know, if you're trying to look at individual houses, you're not going to be able to use a data set that has 100 meter per pixel resolution, unless you have a big house. So here's just some examples of the same area in Kitale in Kenya, and how that looks in different satellite data sets with different spatial resolution. All right, so here's this area in 1 meter per pixel. If we go slightly coarser resolution to 3 meters per pixel, we can see some differences. Also, these are at different points in time, so they don't look identical, but this is 3 meter per pixel from Planet Lab satellite. Here's 10 meter per pixel from Sentinel-2, 30 meter per pixel from Landsat. So you really start to see some differences here. For example, in the Sentinel, we can kind of see these dots, and in Planet, we can see kind of where these individual buildings are, for example, up here in the top right. And then these start to get a little bit blurrier in Sentinel, but still pretty resolvable. Then in Landsat, we can't really see these individual buildings really at all. And the boundaries between these fields start to blur, and you know, things get much coarser. And then with MODIS, this is much coarser resolution. So now we went from 30 meters per pixel to 500 meters per pixel. So obviously this data set is not great for looking at objects, individual objects on the surface. Is used much more for looking at really broad trends. For example, in like vegetation, greenness, and entire areas over the globe. That said, you can imagine as the resolution gets higher, the data size gets way, way bigger. And so, you know, coarser, if you can use coarser resolution data, then you should, because it'll make your data much easier to work with. And so this is also now not looking at the visible. This is actually synthetic aperture radar, or SAR, image from the Sentinel-1 satellite. So SAR is emitting a radar wave and measuring the returned signal at different polarizations. So that's what we're seeing here. The different colors are different polarizations. And so this false color. So you can see like radar is really good for looking at things like water. You see this little smooth spot here would be easily detectable, or I guess that's maybe not water, that's like some other object. But it's good for detecting things like smooth buildings or water, things that have very distinct textures. But with the trade-off that it's very noisy. So we see a huge amount of speckle in here, which is of course a problem that we need to deal with in our models when using that as input. So I'm just going to play this little video while I talk about the temporal resolution. So the temporal resolution is describing the frequency or the cadence of images taken over the same place. So for example, the Sentinel-2 satellite has a 5-day revisit time. So every location on the Earth is revisited by Sentinel-2 every 5 days approximately. Of course, this changes at the poles. The poles have much higher revisit since all of these orbit tracks are coalescing very densely at the top, but at the equator, it's about 5-day. Landsat has every 16-day revisit time. Planet, like I mentioned before, has daily revisit time. So, you know, collectively, especially if there's multiple satellites. So here, this visualization is showing Landsat 8 and Sentinel-2. So you can see Sentinel-2 actually is made up of 2 satellites. So this is how it gets a 5-day revisit time. It gets a faster revisit than Landsat, which is only 1 satellite. Okay, so I'll just flip through these to show our same area in Kenya at different points in time. So here, this is a Sentinel-2 image of this area with some fields in particular on February 15th, 2022. This is on March 17th, 2022, April 6th, May 11th, June 15th, just the other day. And so if I flip through these a few times, you can see that there's really a lot of information in the temporal dimension. So there's a lot that's happening that we can see in there. And that was at a monthly cadence. You know, imagine that we also have daily. And from this satellite in particular, we have every 5 days. I just put monthly to have fewer images, but we'll see some GIFs of higher temporal cadence later. So if you're thinking about how should I choose which data set to use, like I mentioned, we have to think about what is it that we actually want to see on the surface. And so that influences what spectral bands the satellite needs to have in terms of both the number of bands, but also the wavelengths that are covered by those bands. You know, those might be different depending on if you're looking at what's covering the ground versus if you're looking at the atmosphere or at oceans. You know, we're mainly talking about land here, but there's a huge amount of work in atmospheric remote sensing, ocean remote sensing, et cetera. How large are the objects you want to detect? So if you want to detect small objects, you need a higher resolution sensor or higher spatial resolution data set. How useful is the temporal component? So if you're just trying to detect something that's not really changing a lot over time, like lakes, for example, maybe you don't need a high temporal dimension. But if you're trying to look at what is the yield of a maize field based on satellite data, you might want a really high temporal dimension because you want to see how that field is changing over all these critical times in the growing season. And also, what kind of money do you have to spend on this? Because most of them are publicly available. So the NASA and ESA, which is European Space Agency, data sets are typically free. So Landsat's free, Sentinel's free, MODIS is free, et cetera. But commercial sources like Planet or Maxar, which is kind of what you see in Google Maps usually, but you don't know the time of all those Google Maps images and everything. If you want to request your own images at that Google Maps resolution, that's going to cost money. So those data sources can be pretty costly, but Planet in particular does have education and research licenses. So for non-commercial use, you can get a lot of data for free. And another challenge with those paid ones is a lot of times they're contract based. So you can't just necessarily like ask how much is it going to cost me to get like one image of New Orleans. It's like a very complicated thing. You might get a different answer depending on who you are. So that can be a bit tricky. Okay, so how do we get these data into a form that we can use for our machine learning models as input? So the way this happens is in the life cycle of these inputs is first the satellite is acquiring these images, and then these images get projected onto a grid of the Earth's surface based on where that satellite knew that it collected the image. This is called orthorectification, where you're taking this image and putting it like a paper mache kind of over the Earth's surface on top of this grid. And then the image that we get from, for example, ESA or NASA is the tile, so this particular like grid tile, and whatever data for that date was actually present, or like what the coverage over that tile was. So if on June 16th, the satellite took a picture over New Orleans, but the track was like a little bit off of this tile, we're gonna have all this missing data on the side of the tile like you see here. So this is that kind of paper mache thing that's happening. So we get these images like into this gridded format that's defined by the band, the time and date that it was collected, and the location. So then from there, we have to somehow take this image and put it into, or take this stack of images over time and put them into the appropriate size and format, et cetera, that we want to go into our model. So put it in our whatever tensor dimension we want. And of course, all of those have a time band that's not even being shown here, but so these images, these grid tiles tend to be very big. So for Sentinel-2, the image that we get from those data sets directly is 10,000 by 10,000 pixels, just for one date. And so there's a lot of information in that. We're not going to put that directly into our model. We have to somehow take patches of it or do something to transform it into maybe a 1 by 1 dimension. So just each pixel individually, if we only want the time series, or 224 by 224, et cetera, et cetera. So we have to further process that into the dimension of our model input. And in addition to just getting the input in the right size, there's a lot of pre-processing that has to be done to get the data to be what we would call ML ready. So we have to do radiometric correction, which in a lot of cases is already done on the data set and provided for us. So the atmosphere is in the middle of the satellite and the ground. And so the atmosphere can add some kind of distortion or effects that we want to remove to clean up our signal. We have to mask out the clouds. So there's a lot of clouds on Earth, and even more depending on where you are. And so you see in this image on the left, this is a PlanetScope time series before any corrections have been done. So this is before radiometric calibration or atmospheric removal, before we've done any cloud masking, before we've gap filled to get rid of the gaps where clouds were or where these missing data kind of black stripes are, all these things. And often there's even some misalignment that we might have to deal with. There might be some outliers. So we have to do a lot here. But then, so this is an example where, again, on the left, this is before any pre-processing. In the middle is a data set that is available from NASA called Harmonized Landsat and Sentinel-2. So there they've harmonized the Landsat and Sentinel-2 data sets to have the same kind of grid and spatial resolution. And then on the right is the result of doing some very computationally intensive processing to get a gap-filled, cloud-free, totally clean time series, which is really like the dream for our models, but is really difficult to get to. Fortunately, we don't have to do this completely from scratch all the time. There are lots of platforms that have come up, especially over the last several years, to help with taking these source data sets and transforming them into the pre-processed ML-ready versions that we want to use as our model inputs. So, for example, Google Earth Engine hosts many satellite data sets and other geospatial data sets on Google servers. You can do your pre-processing on their servers and nicely parallelized and everything for free, and then export the data. You can export it in GeoTIFF formats, or you can even export it as TF records. There's different options there. And so you can do like images or time series. It makes it really easy to align inputs from multiple satellites in particular. So if you're like, oh, I want the data from MODIS and from Sentinel-2, you don't have to like align their grid systems on your own or all of these complicated things. You can just, it'll align it for you at whatever resolution you want in Google Earth Engine, which is super nice. There are also some other platforms that have come available recently. So Microsoft Planetary Computer is pretty powerful. They've made a lot of updates to that in the last year or so. Descartes Labs is another platform, but I think it's a paid platform, but I've heard good things about it. I don't personally use it yet. And Pangeo is a kind of an ecosystem of Python libraries that have been developed for making geospatial data easy to use. So it includes, for example, a package called Xarray, which kind of makes working with tensors like working with pandas. So it adds like named dimensions and easy interpolation over time or spatial dimensions and things like this pretty easy. And then also OpenMapFlow is a library that we've been developing that Ivan is going to talk about, which in particular is designed to make that dense inference part of the pipeline really easy. And we also have a crop harvest package that we've developed to make it easier to export time series satellite data with multiple satellite data sets anywhere in the world. So when we're using these data, or when we're taking our machine learning models and making predictions and then using the outputs of those predictions, there's some important distinctions from what we traditionally think about in computer vision machine learning. So I mentioned this before, but here, when we're working with remote sensing data, typically we're applying the model in this dense, what we call dense inference paradigm, where we're taking this entire region of data, making predictions over every location within that region and stitching it all together to get a final map. So that's what this diagram is showing here. And so these, basically, we have to do a lot of work to make our inference as well as our pre-processing scalable. So in a lot of problems, we're used to the model training being a really computationally intensive part of the pipeline, and inference is much cheaper. But here, training tends to be pretty lightweight compared to inference because of this setup. But this also presents a lot of interesting new research challenges. Like, for example, how do you evaluate a really dense map like this when you only have very sparse labeled data, and there might be a gap between that? So we'll talk more about that too. So finally, I'll end this section by talking about some things that are important to keep in mind when we're working with this exciting modality of remote sensing data in computer vision and machine learning generally. Spatial autocorrelation is a really important thing to keep in mind, where, for example, two images that are within the same crop field are going to be much more similar to each other than, you know, two images from different crop fields in different countries in particular. So we have to think about what is the independence between images that might be right next to each other from the same location, same point in time, et cetera. And that's really important for how we design our training, validation, and test sets in particular. So we don't want to have this spatial autocorrelation between our training and validation sets or our training and test sets. Otherwise, we will inflate our evaluation metrics. So this is like a huge problem in the remote sensing community generally is, you know, a lot of things have this spatial autocorrelation. So important to keep in mind. Visualization and error analysis are also really important. It's not as easy as with ImageNet or COCO, for example, to look at, oh, which are the ones that I misclassified, and I can look at them all easily at one time, see what some certain trends might be and do some diagnosis. It can be pretty challenging to even visualize the data sometimes, especially because the data are not even like PNGs or JPEGs. It might be a TIFF or a GeoTIFF, which you can't open in preview. You know, you have to use specialized software or load in Python or whatever. So despite that being challenging, and again, there are a lot of libraries, for example, in Pangeo for helping with that, it's super important to do. So for example, if you have, this is an example where we had some blocky artifacts in our output, but by plotting that output map alongside the, you know, we suspected like, oh, this looks like a coarse resolution satellite bias. So there was one data set that was really coarse resolution, which was climate data. So like the precipitation and temperature, which I plot, the grid on the right is plotting. By showing those together, we can see, oh, these blocking artifacts appear to be on the same grid as the climate data set. And that's probably where these errors are coming from. I mentioned this briefly before, but there is a really often big gap between what we get from our evaluation metrics, which are based on very sparse labeled data. Even if we have a pretty large test set, again, it's very sparse compared to an entire dense area map. And so, you know, you might get 95% F1 score and you're like, yay, what a great model. And then you look at the map and it's got all of these blocking artifacts, or it's got like really blatant errors that are just not captured by that sparse labeled set. We have distribution shift or domain shift between sensors, particularly, I mean, sensors, you're like completely different domains often. So you might have a visible satellite or a visible data set versus a radar data set, which will be very different. We have these distribution shifts, especially in space and in time. So, you know, if the climate is changing and there's over time in the long term, but there's also pretty significant shifts between different seasons or individual consecutive years. And so being able to be robust to these distribution shifts as time goes on and we use our models in future years or we use them in different locations is really important. This is just an example of time as well. So here I'm showing like the same date of some fields in Illinois, in the US on June 13th, 2018, where we see a lot of these fields have been growing quite a bit already. And June 13th, 2019, so the same day, but in the next year, things have barely been planted. And so you can imagine if you're using something that's looking at the time dimension in particular, this would be a pretty substantial shift for your model. Another important distinction is that often the labels that we're using, Catherine will talk more about this in a later session, are georeferenced shapes. So we might be going to a location and recording, you know, at this latitude and longitude, maize is growing in this field. But depending on the satellite data set that gets paired with, you know, those might not be all perfectly aligned. So there might be some misalignment between the data sets and our labels. And especially for things like, here's some examples of field boundaries, which are polygons that are georeferenced. Those might be, you know, not exactly aligned on different data sources, which can be a problem. And you also have to think about using the right date for those. So even if I recorded that, there's a building here in 2022, in 2025, the building might be gone, or a forest might be gone, or a crop field might be gone, might be something else. So our labels are not always valid through time. This is actually an important thing with using the Google Maps API for getting images is you don't know the date that those images were collected. So it could have been 2000, could have been 2020. So you have to be careful when you don't know the date and if it corresponds to the date of your label. And finally, existing architectures in computer vision are not typically designed for remote sensing images. So there are important distinctions in these data sets that we're sort of missing out on in a lot of existing architectures. I think there's a lot of space for doing novel research in. For example, the objects tend to be very small that we're trying to detect with respect to the full image. And so this has important implications like how deep your convolutions should be. The visible field or the receptive field for your model should actually be much smaller with a remote sensing image. You don't want super deep convolutions a lot of times because what's on one side of the image is not necessarily useful for what's on the other side of the image in terms of predicting whatever the class is, which is very different from, for example, in this Coco image, knowing that there's a wheel here in the bottom left and a handlebar here in the middle, getting that context in our deep models is useful, but we tend to see shallower models performing better with remote sensing. There's also lots of textures, not so much like very distinct visual shapes in our data. We have these multiple scales, et cetera, et cetera. And interestingly, for a lot of tasks, a random forest is still a very competitive baseline, which I think shows that there is a huge amount of opportunity to innovate beyond what we have from, or what we've developed in terms of architectures for existing vision data sets for remote sensing. So there's a list of resources. This is also on the tutorial page that you can look into if you're interested in learning more about these data. And with that, I will end this session, and maybe while we transition, feel free to come up and ask any questions. But next, Catherine will be talking about Earth observations for agriculture.